Okay, so we talked about SN2 reactions. The comparison is with SN1 reactions. And what the 1 here means is the unimolecular, it's for one molecule, unimolecular for the important or rate determining step. And since it's unimolecular in the rate determining step, but there's another reactant, it sort of follows that this is going to be a two-step reaction. So SN1 reactions are typically 2 or more steps. And the important feature here typically is we're going to have a tertiary substrate is going to favor these types of reactions. So here's a tertiary iodide, and this might be written as 2-iodo 2-methyl propane, right? And you can see how this carbon, the second carbon in the propane, is tertiary because it has 3 carbons attached to it. Carbon number 1, carbon number 3, and the branch off methyl group. So 1, 2, 3, there's where we get our propane from, 3 carbons in a row. Off the second carbon, there's both a methyl and an iodine. So this would also be called t-butyl iodide in the old nomenclature. So we put that in parentheses. And the thing about this is the tertiary group with all these carbons blocking this carbon, there's no way a nucleophile is going to get in there. So what will happen here is that if you put in the right solvent or heat it up or whatever, then the iodine is just going to leave on its own. So it's going to say, it's crowded over there. My bond to the carbon is not that strong. I'm just going to hop off. It doesn't happen all the time. This is slow, essentially rate determining step. You form a carbocation. And this is what we talked about earlier, is that the tertiary carbocations are much more stable. Primary carbocations are very unstable and rarely form in significant quantities. And then you end up with the iodide that's fallen off, sitting around in solution. Now, what often happens is the iodide, being negatively charged, sees the positively charged carbon it just left and hops back on. So there's some sort of equilibrium. This falls apart, reforms. Falls apart, reforms. But then if there's another nucleophile around, and this can be a fairly weak nucleophile. So when you SN2 reactions, you sort of need a powerful nucleophile to go pushing things off. But once you have an exposed carbocation, far weaker nucleophiles can go ahead and get in there and do the reaction. But I'm going to write it out with sodium hydroxide again as just the typical nucleophile. So sodium plus, hydroxide minus. And now that you have a lone pair on the nucleophile, you can go form a bond to the carbocation, and you end up with your t-butyl alcohol. And that'll liberate your sodium plus, and the sodium plus will hang out with the iodide we formed in the first step. So the overall reaction would be t-butyl iodide plus sodium hydroxide goes to t-butyl alcohol plus sodium iodide. So overall reaction, but it happens in 2 steps. First, the tertiary iodide falls apart. There's the arrow saying iodine's leaving with his electrons to make iodide, and a carbocation the carbocation is very susceptible to nucleophilic attack because it's got an empty orbital, it's positively charged, it's looking for a nice pair of electrons to bond to. So this carbocation is an electrophile. So remember, chlorine cation or NO2 cation looking for electrons, electron lover, electrophile, and that makes the hydroxide the nucleophile. Many anions are nucleophiles, they're looking for positive charge. These guys get together, bam, there's our product, tert-butyl alcohol. And the thing that took me a while to get used to with these reactions, like SN1 reaction, is if you want to make tert-butyl alcohol, you can react tert-butyl iodide plus sodium hydroxide. But if you wanted to make the iodide, you'd take tert-butyl alcohol and put an iodide in. And I was like, how does it work that sometimes it goes forward, sometimes it goes backwards? Well, it often comes down to the amount of stuff that's in there. So if there's a lot of iodide, the iodide will trap the carbocation, and you'll get this. So if you had a lot of iodide in solution, they'd fall off, but then they'd swarm back on and be stuck with the iodide. You wouldn't be able to get anything to form from there. But if when the carbocation forms, there's very little iodide, it wanders off in solution, and there's tons of hydroxide, that'll jump on the carbocation, and you'll end up with lots of the alcohol. So if you have lots of iodide around, you get the iodide product. If you have lots of OH minus, hydroxide, you get the alcohol product. So you can often control what your product is, mechanism being the same. The other thing though is that the hydroxide is a terrible leaving group. So in this case, even if the hydroxide was in small quantities, once it bonds, it's not going to fall off. So one of the things we need for the SN1 reaction is we need a decent leaving group. So the SN1 reaction is favored by tertiary substrates with good leaving groups. So SN2 reactions were favored with primary substrates and good nucleophiles because the attacking of the nucleophile on an exposed target was important. The SN1 reaction, where something falls apart first, you need something that'll fall apart better, and you need something that'll fall off and be stable. So we'll talk a little bit more about what favors one versus the other, and you might be thinking already, what about secondary substrates? And that's where it gets more complicated because those are exposed enough that some nucleophiles can get in there, and under the right conditions they will fall apart like tertiaries. So secondaries can sort of do either thing depending on conditions. So if you were taking a more advanced course in this, there would be a lot of detail, and certainly I'd encourage you to go ahead and pursue that if you want chemistry to be part of your life.